Section 2 from Unit 5 is going to define stoichiometry. So in the last section we learned how to balance equations, right? That tells you the relative amounts of each substance during a reaction. The coefficients in front of the substances represent the mole ratios present in the reaction. Okay, so in this example here, 2Fe plus 3F2 yielding 2FeF3. Okay, these represent moles, the 2, the 3, and the 2. So every 2 moles of Fe, 2 moles of FeF3 are produced, right? So every 2 of this produces 2 of this. For every 3 moles of F2, 2 moles of FeF3 can be produced, okay? Or any sort of variety of multiple of this, right? You could have, 4, 6, 4. Or even divided in 2, 1, 1.5, or 1. Now, when we write it as a balanced equation, it has to be whole numbers. But these represent moles, okay? That's what those are. And what we're going to use those moles for is to create ratios. We can determine relative amounts of substances. So if we say we are starting with 2 moles of this, how many moles of this can we make? Well, if we start with 2, we could make 2. So what is stoichiometry? It's the study of the quantitative relationship between the amount of reactants used and the amounts of products formed by a chemical reaction. It's based on the law of mass conservation. Okay, and I know that the words here might be a little bit confusing, but basically it's kind of like how do we follow a recipe? If I start with 2 grams of this and 16 grams of this, how many grams of product X can I make? So here's another example. Let's say we have 4 iron atoms plus 3 O2 molecules. That's going to yield 2 Fe2O3. Okay, so what these means, okay, they're mole ratios, the 4, the 3, and the 2. Means for every 4 moles of iron used in the reaction, 2 moles of Fe2O3 will be produced. Or, if you want to think of it, you could double this. For every 8 moles of Fe used in the reaction, 4 moles of Fe2O3 are produced. And really, things aren't too bad if you're talking about whole numbers. It makes it pretty easy, a 4 to 3 to 2 ratio. But what if I had like 0.363 moles of iron? How many moles of Fe2O3 could I produce? Well, you have to do a little bit more thinking then, because now we're thinking, okay, this one it really operates in a 4 to 2 ratio. So if I don't have a perfect whole number, it's still going to happen in that same ratio. So we need to learn how to do the math with that. So we need to learn to write mole ratios first. Okay, a ratio between the numbers of moles of any 2 substances in a balanced equation is considered a mole ratio. So let's take, for instance, this equation here. 2 atoms of potassium, or 2 moles of potassium, plus 1 mole of bromine atoms, Br2, okay, liquid bromine, yields 2, this is called potassium bromide, 2 KBr. Okay, and by the way, remember, if you don't see a number in front of the substance, we assume that to be 1. Okay, so what does this mean? Well, we can create a bunch of mole ratios here. So for example, for every 2 moles of potassium, we need 1 mole of bromine, okay, atomic bromine. Or we could write it in reverse, since we've been talking about conversion factors being the same thing, just flipped over. For every 1 mole of Br2, you need 2 moles of potassium. Okay, these are equivalent amounts. Okay, we consider them conversion factors. All right, and if you don't remember, we did conversion factors back in section 1.6. Okay, with dimensional analysis. Really, once we get out of sort of our basic chemistry definitions and terms and understanding what an atom is, the rest of chemistry is really just dimensional analysis. Okay, so we can create all kinds of mole ratios here. We could look at it in terms of potassium and the compound that is formed. So for every 2 moles of potassium that you use, you can make 2 moles of KBr. Or for every 2 moles of KBr that was produced, you needed 2 moles of potassium atoms. Okay, and then finally, the only one we haven't done yet is the combination of bromine and potassium bromide. Okay, so for every 1 mole of Br2, we would produce 2 moles of KBr, and then for every 2 moles of KBr that had been produced, we needed 1 mole of Br2 to do that. So we can take any of these combinations of mole ratios to figure out how much we need to combine with something else, if we're talking about the reactants, or how much product can be made based on how much reactant we had. Okay, oftentimes it's kind of like thinking like a recipe about something, right? You can double a recipe to make double the product. If you don't have all the ingredients or enough of the ingredients, you can have one of the ingredients to only make half of the product. Okay, but it basically tells you the ratio in which these things react. Okay, so our goal here is to balance a reaction and then write all of the possible mole ratios. So I'm going to do one with you, and then I'm going to have you do one on your own. Okay, so here we have a reaction of sodium metal with water, liquid water, giving us sodium hydroxide, which is the name of this compound, which is aqueous. It's dissolved in water, and H2 gas, hydrogen gas. Below, I've gone ahead and counted out the number of atoms on each side. Now, typically speaking, you've heard me say, we try to avoid starting with hydrogen and oxygen unless we have no other choice. We like to avoid them because they're usually the last things to get balanced. Well, here we don't really have a choice. Okay, the sodium and oxygen are already balanced, and I've got 3 hydrogens over here and 2 over here. Remember, there's 1 here and 2 here. And so really what I want to do, since this side is lower down than this side, is I'm going to try to make this side larger and see if we can't find a way to get my hydrogens equal. Okay, so what I'm going to go ahead and do, because I know I need more than 2 hydrogens, is let's just go ahead and put a 2 in front of the H2O. I definitely need a higher number on this side, so let's at least put a 2 here. Well, when I do that, I make this now 4 hydrogen, and I've now made this 2 oxygen. Okay. Well, if I look over here on this side, all right, let's not worry about the hydrogen for a moment, just because I've got hydrogen here and hydrogen here. Might be a little tricky to balance. Let's look at the oxygen. Okay, now they're not equal, so let's go ahead and fix that. Let's try to find something to make oxygen become 2. Well, that would be if I put a 2 in front of the NaOH. Okay, now when I do that, it affects all 3 of these things. Okay, so suddenly I now have 2 sodiums. I have now 2 hydrogens here, 2 from that, and 2 from over here. So now my hydrogen total is 4. Okay, and I've already gone ahead and fixed my oxygen total. So I've got 2, 4, 2. Now the bottom 2 things are balanced. The only thing not balanced is the sodium. I've got 1 on the left and 2 on the right. So if I just put a 2 there, okay, that fixes the balancing. Let's go ahead and take a look then at writing out all the possible mole ratios. I've gone ahead and written out the first one for us. Okay, so for 2 moles, we got to combine every possible thing here. So we're going to combine the reactants first. So for 2 moles of sodium, I need 2 moles of H2O to react with it. Or for every 2 moles of water, I need 2 moles of sodium to react with it. So that's the first one. Let's go ahead and then combine the sodium with the sodium hydroxide. Okay, so for every 2 moles of Na, I can produce 2 moles of NaOH. And yes, that is a 1-to-1 ratio, but we are still going to write it with the numbers from the balanced equation. Okay, or we can write it upside down. 2 moles of NaOH are produced for every 2 moles of Na that are used up. And then let's go ahead and do the last one, the sodium combining with the H2. Okay, for every 2 moles of Na, I will make 1 mole of H2, or you can flip that. For every 1 mole of H2, okay, I needed 2 moles of Na to make that. Okay, so now I've got all my possible combinations with sodium. Let's move on to the water. So the water already has a combination with the sodium, right? That is this one right here, so I don't need to worry about combining it with that. Let's go this direction, okay? So now I've got 2 moles of water are needed to make 2 moles of NaOH, okay? Or you could flip that. For every 2 moles of NaOH made, okay, you needed 2 moles of water, okay? So now we've got that one combined together. Now let's combine the H2O and the H2. For every 2 moles of H2O, I make 1 mole of H2, or for every 1 mole of H2 that was produced, I needed 2 moles of H2O to make that, okay? And then I need to look at the last option here. Okay, so we've already combined, now we're looking at sodium hydroxide. Sodium hydroxide's already been combined with Na, it's already been combined with H2O. Now we're just looking at the products, all right? So This one's going to mean that if I have 2 moles of NaOH that were produced, I would also make 1 mole of H2. Or for every 1 mole of H2 produced, I also produced 2 moles of NaOH. Okay, so I want you to go ahead and balance this equation, and then after that, write out all the possible mole ratios, and you'll be asked some questions about it.